Hello everyone. Thank you for joining us today, and let's do this. We are Pavel and Thomas, and our topic is V2GEvil, Goats in the Wires. I, with Thomas, do this for my master thesis, and I successfully finished it earlier this year, so thanks to Thomas. And we will present our tool today and whole journey, which was for all of this. And my name, as I said, is Pavel Khunt. I'm currently working as the cybersecurity researcher in Auxilium Pentest Labs, and my colleague is Thomas Sermpinis.
Yeah, I'm Thomas Sermpinis. Many of you might know me as Grow Tom. I'm the technical director of Auxilium Pentest Labs by day and security researchers by night. I was the supervisor of the thesis for the Czech Technical University that we did it with Pavel, and yeah, as discussed, we successfully finished it, and we are keen to, we really want to share with you this information today. And yeah, basically to start off, I want to give you an understanding of what we will get out of this talk. And basically, our main goal is to analyze the state of cybersecurity in the automotive industry and get an in-depth look in the EV architecture specifically. And this undeniably emerging attack vector that we see outside in the streets. We want to explore and understand the communication protocols used in EV charging today and introduce you to the security tool that we built, which is called V2GEvil, the result of the thesis we did, and create a reference point for EV security research and evaluation, something that we feel that our industry is lacking, alongside other vectors in the automotive security landscape, of course. So let's start by getting introduced to vehicle cybersecurity and understand the current state of this. And it goes without question that the automotive industry cannot be considered new, of course. We're basically talking about 100-plus-year-old mechanical engineering industries, and hopefully you see where this is going. The constant need for connectivity and technological aspects of this pushed those companies to make a restructuring and start implementing technologies that didn't have the know-how or the capacity to do so, which is good for us. We have work in the end, but really bad for the security and safety of the affected vehicles. On the other hand, you have all these startups that started as technology companies first, which have a way better security posture and culture. But the industry as a whole struggles for the last decade, and to be honest, I cannot see a clear light in the end of this tunnel. And isolating the part we will focus on this talk, we have the emerging industry of electric and hybrid vehicles, mainly developed to decentralize pollution and make better use of clean energy solutions. And additionally, you have several advantages in comparison to internal combustion engine vehicles, as the example of the heavy gains in efficiency and speed and others. And while early models used basic charging, the last decade, charging standards are applied and enforced in many ways, which led to the standardization of the ports, protocols, and underlying data in a wide range of applicability for different continents and standards. This, of course, in addition to the digital communication needed during charging, expanded the attack surface of the vehicles as we knew them before, and created new attack vectors that we can start playing with. What I'm saying is not something new, of course, or groundbreaking by any means, but the state of EV charging security is barely touched topic by researchers, which during our work we felt that it definitely needed a bit more love. And here we have a really simple representation of a modern vehicle, which normally includes a bunch of interconnected ECUs, electronic control units as we call it in our industry, responsible for different functionality inside the vehicle. This can be from simple headlight ECUs to huge DC-DC converters. What we see, though, is that while the vehicle till now was reasonably isolated by the outside world, now we have a newly externally accessible port which connects to the charging stations. This leaves a big room for error, and if not properly implemented and designed, several unexpected instances can occur. And here we have a more realistic representation of a modern vehicle, as it needs to be said that it's not only the charging port, but other interfaces are introduced that can expose our vehicle and need special consideration on the architectural and design parts of developing a vehicle. While this might not seem as important, there are numerous instances that architecture played a big part of how severe our findings are during a pen test or research projects, and how in the end can or cannot affect the safety of the driver, the passengers, and the pedestrians. And as we keep diving deeper and deeper, let's discuss a bit about charging in terms of vehicles and the automotive industry. And first of all, there are several charging methods, including conductive, wireless, and some exotic ones that are only seen in some manufacturers, like battery swaps and bidirectional charging between two vehicles. On top of that, there are different types depending on the needs of the user and the capabilities of the vehicle, including AC and DC charging, supplying different advantages and disadvantages, as we will see later. And finally, during the charging, there are also different modes of charging. Basically, there are 3 modes focused on the AC, and the 4th one is mainly focused on the DC. Starting to talking about the boring stuff, and something that you don't even need to look at because you will get dizzy out of all these ISOs and the standards. There are a lot of different standards out of them. And as our main focus is the Combined Charging Standard, or CCS, mainly focused on Europe, we just have this undeniably big list of standards for different levels of full implementation, ranging from the connector itself, what we connect to the vehicle, to the high-level communication needed between the EV and the charger itself. This CCS standard is basically an effort towards a single unified system for electric vehicle charging, which in the latest news, you might not agree with it because there are several new things in the industry, and one of them is that basically a lot of manufacturers in the US trying to adopt the Tesla standard alongside others, and basically different continents have different standards for charging in the whole stack of communication and the OSI layer in general. And as we look at this slice of the CCS connector, we can distinguish several pins. First of all, the AC phase 1 and 2 pins, which are the power lines that provide the alternating current to the vehicle. We have the neutral pin, which completes the electrical circuit. The PE line is basically a safety feature that helps to prevent electric shocks. And then we have the CP and PP lines. Basically, the CP line is the one managing the communication that we will be interested later, because we want to attack this power line communication, high-level communication, in order to perform our testing. And finally, the PP line, which ensures that the correct connector is used and provides information on the current carrying capacity of the cable. Then we have the DC charger, mainly used for faster charging of vehicles. Basically, the AC can be used for overnight charging for long periods of time, and the DC for fast burst over a road charger. And basically, it's also known as Combo 2, and it incorporates the same pins as the AC charger, but adds 2 additional pins specifically for the DC charger, for the fast charging. Here we can basically get an understanding of how this works internally in the different implementation of DC and AC charging. On one hand, we have the DC charging when the power electronics for conversion of current exists in the EVSC side, so in the charger. While when we want to use the slower solution, the AC charging, the conversion is happening inside the vehicle itself by the onboard charger. And this gives us an understanding of the communication channels also that exist in all those scenarios, really important, as we will see later for our research. Yeah, basically we clearly understand now that charging is not only simple power transfer in vehicles, and data exchange is also happening under the hood. Many times with important information like payment details, voltage and current requirements, time of charging, and other things flowing there. And to get a better understanding of how this communication is structured, I will pass it now to Pavel.
So first of all, for start the charging communication, we need the plugin. So you need the CCS inlet and CCS connector. And then for some charging, for all of the charging modes, can start the low-level communication. And if these preconditions are matched, like the duty cycle 5% and some specific measured voltage that indicates that the vehicle is in state B, then can be triggered the high-level communication. And this high-level communication is that what we are aiming to. So this is how my thesis journey began. And first of all, we need some description of the low-level communication. Maybe it will be a little bit boring, but I had to say so, sorry about that. Low-level communication, it's also called the basic signaling, which is basically physical signaling over the CP and PE pins, which is also called control pilot circuit. And there is used voltage measurement and the pulse width modulation signals over this line. And based on the voltage, there is like the EVSE, which is electric vehicle supply equipment, can indicate or can see in which state is the EV, because the EV adding the resistors to the circuit can control the voltage in the circuit. So here is the table. For example, the state B is that the EV is connected and is not ready to charge, and for example, the state C is that the start can be, charging can be started. Also, there is the EVSE side, which controls the duty cycle, and with the duty cycle, it can inform the vehicle about the available current or what is the maximum current, and it can even force the high-level communication. That is, forcing high-level communication is done by setting the duty cycle to 5%. So we are interested in this part, that EVSE set the duty cycle to 5%, and then the high-level communication can be triggered. So as you could see, the low-level communication is not so interesting from cybersecurity perspective, but we need to know about it because it triggers the high-level communication in which we are interested. So let's explore the HLC, high-level communication. First of all, why do we need it? Why it's not enough or sufficient to have the low-level communication? That's basically because with the growing the number of electric vehicles and complexity of our energy ecosystem, we need to exchange some more information. For example, for the DC charging, we need to exchange more specific information to avoid the battery damage, because every vehicle has different battery and it needs some specific voltage value or the current value and so on. And it's also, this high-level communication should serve for enhanced user experience, which is basically, for example, plug and charge. So in the future, you can just plug your vehicle to the charging station and the identification and payment is done out of the box over this high-level communication. So, as I mentioned, the precondition for high-level communication is the low-level communication with some specific voltage measured and with the specific duty cycle. High-level communication is applicable only for the charging mode 3 and 4. Charging mode 3 is the last AC one, for which the high-level communication is optional. But as I mentioned, for the DC communication, it's mandatory because we need to exchange this information about the power, like power management, like the voltage and so on. And this communication is handled by EVCC and SECC, which is EV communication controller and supply equipment communication controller. And these protocols for high-level communication are defined in this ISO 15118. So let's start with this ISO. The full name of this ISO is Vehicle-to-Grid Communication Interface. Vehicle-to-Grid has acronym or abbreviation V2G. That's also why we called our tool V2GEvil, because it's focused on evaluation of the V2G communication. Also in the ISO is defined that the communication is done over the PLC, and there is some slack, which is some setting data link layer, which is defined in this home plug green physical. So first two layers in the high-level communication are defined in the home plug green physical, and then other layers above. First of all, the network is over classical IPv6, then it's used UDP, TCP, or TLS. Then there is this protocol V2GP, which we'll explore it later. And for presentation layer, this is the EXI, which is efficient XML interchange, which is basically binary encoding for XML messages. For you, you can see how the specific layers are defined in the different part of the standards, and we are mainly focused on the ISO-2, which defined the third layer and above. So as you can see, this is like, there's a lot of protocols which are used, and so this is more complex than the low-level communication, so it's also bigger space for mistakes. So that's why we are aiming on this high-level communication. And we can focus now on the V2G communication flow, which starting with the state E, which indicates that the EV is not connected. Then you connect the EV to the station. Then it's indicated with the state B. It's okay, I am connected and not ready to charge yet. And after that, with this duty cycle 5%, it's indicate that it should force this high-level communication. So first of all, there's this establishment of IP-based connection via PLC, and then the communication using the standard protocols like UDP can start. So first we have the SDP request and the response. I will explain every message later, so this is just the high-level overview. And this SDP request and response is basically to find the proper TCP port and IP address to communicate. Then we have V2G EXI messages, which is for exchanging the charging information like the payment details, identification, authorization, and so on. Then there is exchange to, let's start, over these V2G EXI messages, there is exchange, let's start the charging. And then also the low-level communication indicates it to this EVSE controller. So now the charging is started, and during the charging, there is exchange of the charging loop information. After the charging is completed, There's also the change to the state B. After that, there are some V2G messages, which are basically for acknowledgement of that the session stopped. All of these are V2GTP messages. So now that you know how the V2G communication flow looks like, we can focus on the V2G messages PDU, which basically consists of the header and the payload. And header is 8 bytes, and the payload length is variable. So we need this because with our tool we need to communicate with the EV. So we needed to do all of the exploration of the message structure and so on. So here's how the header look like. The most important part for us is the payload type, because based on that we can parse the specific information of the message to know which is the payload. And so the payload types, there are basically 4: the SDP request, SDP response, and EXI encoded V2G messages. And there is also space for some manufacturer-specific use. And first of all, we need to understand what is in the SDP request. The SDP request, it stands to SECC, Discovery Protocol, which stands to established, or EV requires some security and some transfer protocol. And this SDP request looks like this. This is the payload type, the yellow one, which indicates that this is SDP request. And first byte of the payload is requested security. It can be TLS or no TLS. And the second byte indicates the transport protocol. This message is needed for our enumerator module, because based on that we can enumerate if the EV requires the TLS or not, or what is the transport protocol. Then for the SDP request, the SECC responds with the specific message. It contains the IP address, port, and security byte and transport protocol byte. This information the EV use for next connection to the TCP port, and the SDP response looks like this. So there are all of the information like IPv6 address for the connection, the TCP port, and the security, and the security byte and transport protocol byte is always followed. It always follows the request message. After this exchange of the SDP messages, if the EV accepts the SDP response, it can connect to the SECC, to the specific IP address and the port, and establish this TCP or TLS connection based on the previous security byte and transport protocol byte. After this establishment, there can be done the V2G messages exchange. And that's with our tool, with the fuzzer specifically, we are aiming to this V2G EXI messages. I will explain it in the next slides, why we focus on these messages. So basically, with the EXI encoded V2G messages, we have 2 types: the application layer protocol handshake messages and the V2G application layer messages. The protocol handshake message is for the exchange which application protocol should be used, and the application layer messages are like the identification, payment information, load leveling, some energy transfer, control information, and so on. So why are we aiming to these EXI messages? Because there's the V2G message concept, and it's based on the shared XML schemas, and because basically the V2G message is XML document, and for the transfer you need to encode it to some more efficient data structure for transferring over the TCP. So we are aiming to decide when, on the EVCC side, when is done the structure coding and decoding, and also the content coding and decoding, and on the conversion to the data structure. And that's the aim of our tool, that we are fuzzing the information in the messages, like the values of the parameters, and aiming like to cause some failures in this process. Here you can see how the plain XML message can look like. So it's basically the XML document. You can see that there is the header and the body, and on the bottom you can see also how this message is encoded to the EXI data stream. We also need to know how looks like the V2G application layer protocol message. So the EVCC request or offer to SECC some specific application protocol and version and so on. Then the SECC responds to this request and choose one of the requested application protocol. And why I'm telling you this, it's because our enumerator tool is focused also to extract all of the information which are offered from the EVCC. Here you can see how this request looks like. So basically, the EVCC can offer multiple application protocols, and in the response is one specific schema ID, which was also in the request, and then it indicates that there was successful negotiation of application protocol. And finally, we can move to the V2G application layer messages, which are all of the other messages in V2G charging communication. As I already said, like for identification, exchange, power information about the power transfer, like the voltage and so on. It consists of the header and the body. Here you can see the example message of this body, and basically we are aiming, for example, with our fuzzing tool, to fuzz every single parameter in the message, and then it can cause some failures on the EVCC side when it's trying to parse first the EXI to XML, and then XML to some internal data structures. So now we will present the testing environment, and it's Tom's turn.
Yep. So yeah, understandably, to approach this, the whole stack that was described, we needed some equipment. We needed some testing environment to physically connect to this port. And for us, the tool that worked and supported us during this research and during our penetration testing is this DLAN GreenPhi eval board with the GreenPhi module, and it gives us the ability to send our messages over Ethernet, which is later bridged to the power line communication. It can, of course, be used for normal PLC communication over the wall, but for our use case, the applicable lines were discussed previously. It was perfect. And an important aspect of this board is this Qualcomm A7000 chip and the GreenPhi firmware, which basically allows us to supply the data link layer to our application to avoid building it ourselves. So we invested time to the rest of the OSI layers. Here we have a shot of our complete development setup, where one board acts as the vehicle and one as the charger or EVSE. There are several ways that we can perform the PLC communication, as you see, but we chose to use the coax cable as it will also be more appropriate for use in a real-world scenario to avoid interferences from other cables. And to conclude, you will be surprised if I tell you that many of these cheap Chinese controllers for Ethernet over power line use the same Qualcomm chip. And if you are on a tight budget, in most cases you can reflash this chip with the same tools and the appropriate firmware and run our tool with a budget of around 20 euros. All of this, we're referring to the first two layers. For the rest of the layers, we used as a reference the joint operating system for EV chargers, or Joseph, which is the start, which in the start we used for both the EVCC and SCCC parts in order to properly implement all the parts of the communication. And later on, we developed our own malicious SCCC part to test against the EVCC reference implementation and the target EVs that we're testing on our penetration testing endeavors. And now we will move to the demos, finally.
No, to the intro.
Excuse me?
To the intro of the tool.
Yeah,
Demos
intro of
will
the
be
tool
later.
and demos, so we can have some proof that we actually developed all this.
So I hope it will be more fun than before describing the ISO and so on. So finally, we managed to implement the V2GEvil tool, which we aim to be the modular tool, and therefore we have some modules. The most important is V2GTP module, which implement basically the V2G transfer protocol. And now I will describe how was our approach like step by step with the implementation. So first of all, we needed to implement the V2GTP module to be able to parsing the V2GTP packets, to decode them for decoding EXI message to XML, and vice versa. We used V2G decoder. And to verify if our implementation of V2G transfer protocol was successful, we also developed the sniffer module, and this sniffer module we tried on that reference implementation that Tom already mentioned. And the sniffer module is capable to live sniffing and also the static sniffing of V2G communication, so it's like any other sniffer for some others protocol. It's also offers decoding and some filtering capabilities. Then we move forward to the message module and the station module. We do it both at the same time because they have too close relationship. So basically, the station module is our malicious implementation of SECC, and to be able to properly communicate with the EVCC, we need this message module which defines some dictionaries to have the proper responses for the requests, because we cannot do it like in the runtime because we don't have the real station with the real voltage values and so on. And the station is the core for security modules. So on top of the station, we build, first of all, the enumerator module, which is able to enumerate the TLS, like if the TLS is required by the EVCC or not, and if the TLS is used, what is the TLS version or TLS supported cipher suites. Also, as I described the application protocol message, it was because the enumerator module based on this request is able to capture all of the information about the application protocols which are offered by EVCC. And also, if you want to add any other V2G EXI request, you can simply add some other functions to this module or methods in Python. and it can be also enumerate the parameters and values in this request. Then finally we implement the fuzzer module, which is testing the robustness and resilience of the EVCC implementation. And as I said before, it focuses on the part which is the parsing and decoding the EXI message to XML and then to the data structures. So with the fuzzer, we are basically sending some invalid values for some parameters. We have different modes of this fuzzer. The most important and interesting is the config mode and the messages mode. And as I said, we focus on these parsing issues and that we can cause some message processing failures. And finally, there will be the demo part. We will start with the sniffer module. So first of all, we have the reference implementation of SECC. We start the running, then we start the sniffer. And we run it only with the V2GTP option, which basically parse the TCP raw data and interpret it as the V2GTP. And then we start the EVCC, also the reference implementation. And now you can see that EVCC was connected to SECC and the message exchange started. And yeah, I can stop this. And this is the output of the tool. So we can also put it instead of only the V2GTP option, the decode option, and it's more like for humans. So you can read if it was the SDP request, what is the security byte, what is the transport protocol byte, what does it mean, and so on. And also for the V2GXI messages, you can see this, how it looks like the XML document. For example, here is that the first message of V2GXI exchange, the supported app protocol request. So this was the sniffer, and the first time it was like only for verify our implementation. So then we implement the V2GEvil enumerator module, and also here's a demo. So we start the enumerator module as all, with option all, which should enumerate all of the information that I already said, like TLS version, TLS cipher seed, and support or required protocols, application protocols by EVCC. So the enumerator module basically start our malicious SECC and then wait for the connection from the reference EVCC. After that, we can see the result. As I said, there is offered supported app protocols. In this case, it's only one. And then on the bottom, you can see that there are the TLS check results, that in this case, the EVCC requested the TLS and transport protocol was TCP, and the TLS version was 1.2, and also the negotiated cipher suite, and so on. So that was the enumerator module. And the last security module is the fuzzer, which is most important. So in this demo, we run it in the config mode. So in the config mode, you can basically specify which message and also which parameter you want to fuzz, and there are also some specific mode for specific parameters, because you can have like parameter which is simple type, for example, the integer or string or base 64 and so on. So also in this case, when we start the fuzzer, we start first our malicious SECC, which are waiting for the SDP request. Then it responds with the SDP response. And then the EVCC making the connection, so all of the initial messages are exchanged, and then after some time we fuzz this message which is called service discovery response, and as you can see, for example, the response code, which is here, it's some, you see the number, and it's usually like the integer, but in this case it's, for example, the overflow of this integer and so on. And for example, in the payment option there are also some, let's say, invalid values. And this, on the EVCC side, it caused the error. And this, for this EXI decoding error, we can have some other modules which will further exploit these issues. But at the time, we only implement like this fuzzer module, and other modules can be built on this fuzzer module to implement also some exploitation steps. We have also some screenshot for the config module, which is aiming only one specific message. So in this case, it's the same, like service discovery response, the details, like which parameters and which values should be fast, you can also specify in the config file. So here is like the start of the malicious station. First of all, there is the normal exchange of the, or proper exchange of the proper data. First of all, there is the request of the application protocol. Our SECC send the proper response with the successful negotiation. Then we can start the communication. We also didn't fuzz the first two messages, which is the application protocol request and response and session setup response. And then you can see that there is also fuzzing this service discovery response. It's again invalid values for all of these parameters. But in this case, we caused the different EXI decoding error, which is specifically, it was thrown the exception by the Java, specifically the unmarshal, which the unmarshal can be vulnerable to XML, external entity injection attacks. So there is also the space for further exploitation of this part. But as I said before, we only implement like the fuzzing, and then we can build also some other modules which are like for the exploitation steps. And basically the unmarshal has some handful like unmarshal methods that read the source of the XML data and binds its values to the new instance of the Java object. So that's like this problem that I mentioned that we are aiming to, like the parsing and the decoding. Yeah, so that was all for the demo slides, and Tom can continue with the
So we can slowly conclude. I can see that you're all hungry. And of course, as you saw, this tool is not perfect, and that's why we're planning to open source it after our DevCon talk, which basically, with your help and with our constant support for this tool, there are several enhancements that can be made, which can result in a really amazing collection of tools and modules that will help the EV side to get more secure. Some of the enhancements that we thought of, like when we first all provide the full suite and full control over the whole process of the charging communication. And additionally, fuzzing of the PDU structure, discovery of the manufacturer-specific messages, and many others can be implemented. We will try to include an exhaustive list of our ideas of how we can extend this tool on our repository, and if someone is interested, it can, of course, directly contact us and help us build a better future for these EV vehicles. And from our end, we have to stress that communication in EVs hasn't reached its assumed potential. With bigger needs in the future, more sensitive data will start to flow and subsequently parsed by both EVs and chargers. This, alongside the fact that not a lot of open source tools are available to cover this attack vector, pushed us to build a tool that we would like to act as an easy way for people to get introduced and start researching both EVs and chargers in an efficient and modular way. So, thank you.
All right, so thank you for the great talk. Any questions from the audience?
Yeah, thank you for the great talk. Regarding the TLS encryption, how is the certificate management done in this world? So, what is happening there? Is there somebody around bringing the certificates to the charging station and into the cars, or can you shed some light on that?
No, usually there is PKI infrastructure on the automotive side. So basically the manufacturer has either their own infrastructure or they have some kind of infrastructure that they can both issue or manage certificates on the EVSE side and on the vehicle itself. How it's handled on the ECU side internally, this is a bit more tricky, and it has to be reviewed always because it has a lot of points of failure that we can isolate. So usually it happens from the PKI infrastructure of the manufacturer.
Okay, thank you.
Further questions?
Maybe I have one. So maybe this also goes along with the other question about TLS. Your tool, as I understand, focuses right now on fuzzing the vehicle itself, or is it also capable of doing the same thing to the charging station? Or would you need to have like a valid certificate that an automobile has to authenticate yourself to the charging station to even start that?
Okay. So first of all, at the current state, we are only focusing on the fuzzing the EV, but it's a little bit, let's say, not more difficult, but more complicated because in this case, you can only fuzz in the responses. So you have to basically wait for the request and fuzz only the response. But we also wanted in like the next step to do it like vice versa, to implement the EVCC side, and also I think also there is the bigger attack surface to attack the station. But we have like the base, like the V2G transfer protocol implementation can be used, so we just will add some new modules, which will be the like malicious EVCC, and then we can also use that fuzzer for that.
And that was also one of the ideas of why we needed to build it in a modular way.
Yeah.
Both for extension on the security side, but also for extension on the EVSE side, as you said, so it's a really good question.
Cool, thank you.
Thanks.
All right, any further questions?
Yeah, thanks for the talk. You mentioned one Qualcomm chipset which was used for most of the EV. Does it mean we have exactly the same behavior on all vehicles, or is it something that the EV manufacturer can modify? For example, is it without TLS for all your tests you performed, or did you see someone using TLS?
On the specification, correct me if I'm wrong, but on the specification, it's not strictly mentioned that you have to use TLS only in specific scenarios that include sensitive data. Okay. So if you transfer sensitive data like credit card information or any other username and passwords or anything like this, then you are forced to use the encrypted communication channel.
Okay.
Yeah, and also like one part of our malicious station can also try to, in the SDP response, it will say, I will not support the TLS, and like one test case is if the EVCC accepts it, although it firstly tried to initiate the TLS connection. Like, what I mean that you can try to force with the station that I'm not supporting the TLS, and if the EVCC will accept it, and if it will exchange the information, you can basically, like, it's the vulnerability because it will exchange the payment details in the like plain text or plain TCP. And the TLS, it's used only like, as Tom said, in the specific scenarios, which is, for example, the plug and charge, that you basically plug your vehicle to the station, and then there's establishment of TLS connection, and over this TLS connection everything is done over it, like identification, what is the need, like I need this power in like 1 hour or 2 hours, and then there's exchange of the payment details, like the station will change the recipe, and then it's based over like the certificates. And this certificate will be for every customer of some manufacturer of the electric vehicles, and every car will have its own certificate, and you will basically manage this payment by this communication. So that's why we need the TLS.
Okay, and it is mutual authentication, so meaning with a certificate at both sides, or only one way?
I think that in the standard is that you have this public key infrastructure, and the verification is done on the EVCC side if the EV communicates with, let's say, the proper station with the proper certificate.
Okay, thanks.
Hi, do you have any information about the station that has been manipulated to grab this information?
Yeah, so basically there are several, there is a lot of research on the EVSC side, so on the charging, because actually there are, like Linux systems that implement PLC controllers on top of them. So there are several people that hacked into them in order to manipulate data like this. From our side, I can say that before we had this, and before we had a way to connect to the port, to the CCS port, or to any other port that supports this, we actually had a charger which was routed, and through the PLC module, we were able to communicate really easily. It was like an Ethernet interface that we just managed the communication. So this was our solution before. Now we needed something more modular, which we can edit successfully, and we can build it ourselves, and also for the researchers to not need to like buy a whole charger in order to start researching these kind of things.
Additional question on your hardware. If I'm not mistaken, if I saw it in the slide correctly, there was just some coax cable on there. Now you said you can plug it in everywhere. So is the hardware in a state that I can connect a Type 2 connector to it and just plug it into the EV? It will handle the lower layer initialization, yes, and we can go right up to the fuzzing part?
Yeah, so basically we have this solution, but basically the tool and this solution there is built for the high-level communication. We can implement the lower layers, of course, but this is just for the high-level communication. Also, the coax cable is just for the lines that are handling the PLC. That's why I said you can connect it everywhere, because if you see, if you see here, the black box is actually a normal power plug that goes to the power socket in the wall. So you can perform the same thing over the home network, the home power lines. And at the same time, you have also two normal lines with with simple cables, and behind that you have the coax cable, which, as I said, we used it because we want to avoid interference of other signals and like big currents that can flow on these charging cables.
But can I start to talk to the vehicle even before I did all the other communication on the lower layer parts?
Yeah, like that's the one thing that we will need to have something which will we communicate on the low-level communication, which was the basic signaling. So, like to send the specific voltage and to measure it, and the EV will add the resistor, for example, to convert to the state C. I think it was like 6 volt. When we measure the 6 volt, we will send the pulse width modulation signal with specific 5% duty cycle to inform the vehicle, okay, now we need this high-level communication, and then we can use like this board and this connection, like these 2 pins, like the CP and PE, to create the circuit. And with this module, the like physical layer is done over the PLC, and the data link layer is done with the firmware in this module, which basically implement the Slack. There is some establishment of the, let's say, data link and over the MAC addresses and Ethernet, and then on top of that, we working with our tool, which basically implement the third layer and above.
I see, thank you.
Yeah, and this is a limitation that we will for sure mention on the tool, and we want to build an all-in-one tool that, as you said, you plug it and it works. But maybe next year in Troopers or somewhere else.
Yeah, because first of all, we needed like to prove if there is some space, like to mistakes, you know, like to try the fuzzing and so on.
I think there was another question in the front.
Maybe a very short one. So I'm not in vehicles and so on, but was there ever a solution where you put all this into a cable and build a rogue cable, so that people, because people use their own cables on the stations, right? So yeah. Could we build a cable that steals credit card information and supply it at the shop to the cars, so swap them, or?
Yeah, it's similar to the answer from before. It's yeah. Because these uses, for example, the reference implementation, and needs a system behind it, we can assume that this system is a whole charger that is compromised. Like it's the same thing as building the cable. We have the cable to test it ourselves in our lab, but it's not a ready-made solution that I can present right now because of several restrictions. So this will be presented on the tool, and I hope that with the help of the community and our effort, we will have this final solution, not for malicious users, but for researchers.
All right, thank you very much. I've got 2 announcements to make, but first, thanks again for having this great talk.
Thank you.